I'm Jonathan Tomkin from the University of Illinois. In this lecture we're looking at recent, current and future climate change. This figure shows a lot of data. Let's examine it. There are three sets. All the data shows the difference in temperature degrees Celsius, and so remember 1 degree Celsius is about 2 degrees Fahrenheit, compared to the average global temperature in 1950. So a value of -1 on the y-axis means that it was 1 degree cooler than the average for 1950. This is known as a temperature anomaly. The top graph is a compilation of several different sets of instrumental data. And these record information over the last 300 years, ever since we had instruments. Before this, there was no reliable instrumental data. We didn't have reliable thermometers. Let's focus on this set of information first. The black, red and yellow lines are different calculations for the global temperature anomaly, and they're from different sources. They do show the limitations of instrumental data. We only had precise climate measurements since industrialisation, so the global instrument record only goes back to around 1850. Before that we only had spotty data. And although there is a longer set of data from Europe, note the yellow line here, even that doesn't go back too far. What has the change in temperature been over the last 150 years? The black line has increased from an anomaly of around -3 degrees Celsius in 1850 to around +0.5 degrees Celsius in 2005. This means there has been an increase of just under 1 degree Celsius, or about 1.5 degrees Fahrenheit, in the last 400 years. Let's focus on the middle figure. This goes much further back in time, to before 800 AD, so over 1200 years ago. The black line is instrument data, and as you can see, it runs out. But we have different sets of proxy data, the coloured lines, that go back much further. These proxies are less precise than instrument data. They rely on making assumptions about how the climate changed natural processes. But they provide climate data that goes back much further, so they're very important to our understanding those earlier periods of Earth's climate. From this data, we can see that different proxies vary, suggesting that there is maybe error in this proxy data, or that different places in the Earth experience different changing climates. Not all climate change is global. Sometimes there are local climate changes from place to place. Interestingly, the proxy data broadly agrees with itself and with the instrumental data. The proxy data suggests that the past was generally cooler than it is today, between 1 and 0 degrees Celsius, or about 0 and 2 degrees Fahrenheit. Notice that there was a big change in both the proxy data and the instrumental data around 1850, when the anomaly, instead of being a negative number, became positive. We saw this big increase in the temperature of around just under 1 degree Celsius. The reason why global temperature has changed so much since 1850 is because of industrialisation. The vast majority of climate scientists believe that the addition of additional greenhouse gases to the Earth's atmosphere has increased the Earth's temperature. Examples of greenhouse gases from industrialisation include methane and, crucially, carbon dioxide. The Industrial Revolution became widespread in Europe in the 19th century, but then spread to much of the rest of the world. And in fact, it's global today. Industrialisation requires fossil fuel energy sources, and by using these sources, by burning oil, gas, coal, we've added carbon dioxide to the Earth's atmosphere. As we can see in the figure, the amount of energy that we've used by burning coal has increased steadily from the 1850s. But other energy sources have also become very important, particularly in the 20th century, natural gas and oil. And these have become ever-increasing contributors to the Earth's natural greenhouse by adding carbon dioxide to the atmosphere. Here we have a figure taken from an ice core. This ice core trapped bubbles of air from the atmosphere over 400,000 years. And so by measuring the concentrations of carbon dioxide in each of these bubbles, we can see how the amount of carbon dioxide has changed. In 1950, there was around 280 parts per million of carbon dioxide in the atmosphere. Today, we're at over 380 parts per million. And looking at this figure, you can see that the level in 1950 was already quite high to begin with. In fact, there is more carbon dioxide in the Earth's atmosphere today than there has ever been in the history of human life on Earth. I should point out that there have been periods in Earth's past, before humans had evolved, that had higher levels of carbon dioxide than are currently observed. Carbon dioxide in the Earth's atmosphere has steadily increased in concentration over the last few decades. This is instrumental data from an observatory in Hawaii. The light blue line is the monthly values, while the dark blue line is the yearly average. The yearly average continues to go up. Notice that the monthly value oscillates. Can you guess why? It turns out that natural processes are still involved in regulating the Earth's atmosphere. The large northern hemisphere's deciduous forests absorbed carbon dioxide in the spring months, but then they emit it again in the fall as leaves decay. This demonstrates that the natural system also influences the composition of the Earth's atmosphere, but it also shows the limitation of that natural system. The natural processes of the Earth cannot act quickly enough to absorb all the additional carbon dioxide that human activities are adding to the atmosphere. As we learned in previous lectures, adding carbon dioxide, a natural greenhouse gas, to the Earth's atmosphere should change the Earth's climate. We've seen this data for temperature in this lecture. The Earth's temperature is warmer today than it was 125 years ago. But can you think of other examples of how increasing carbon dioxide, which should increase the natural greenhouse effect, which should increase the average global temperature, should influence the Earth? Let's look at some examples. One thing that we would think is that warmer temperatures would mean less ice, because ice would be more likely to melt. This has been observed in many different places. One example is Arctic sea ice. This figure shows that 2007 had the lowest Arctic sea ice ever recorded, and in fact this is the lowest amount of Arctic sea ice in human memory. This trend has not changed. In fact, this year, 2012, saw even lower amounts of ice in the Arctic than was observed in 2007, a new record. This is the lowest amount of ice observed in the sea ice in the Arctic in human history. Similarly, mountain glaciers have also shrunk in size. Although it varies from place to place, almost every region in the globe has seen significant shrinkage in the size and extent of mountain glaciers. Glacier National Park in the US has lost almost 3/4 of its ice volume in the last 150 years. This sequence of photos shows the shrinking of Grinnell Glacier. Note that the lake has appeared as the ice has melted, and that the ice, which used to sit hundreds of feet above the valley floor, is now much lower. Another consequence you might expect is rising sea levels. This is partly because we're seeing land-based ice melt and return water to the oceans, but it's also a consequence of the thermal expansion of water. When we make something warmer, it expands, and this is true of the oceans. Sea levels have increased around the world, and over the last 100 years, this has been about 200 millimetres. So in other words, sea levels are around 200 millimetres higher. That's about 8 inches. Recent sea level rise has been faster than was observed earlier in the 20th century. So we expect that this rate of sea level rise should increase through the 21st century. And of course, there are many natural biological systems that are key to the climate. Using historical records, researchers have determined that Japanese cherry blossom trees are blooming earlier now than they did in the 19th century. And we see this in many other systems. So what does this suggest for the future? Well, it turns out that this is tricky. Prediction is difficult because not only do we need to understand the Earth's natural systems, but we also need to predict what people will do. Will we continue to burn as much fossil fuels or more in the future as we have in the past, or will we change our industrial methods? As a consequence, international bodies have used different scenario estimates to determine what would happen to the Earth's temperature if humanity decided to do different things. Let's look at this figure. Here we can see the 20th century data in black, and then there are predictions for different climate futures. The pink line suggests that we add no more carbon dioxide in the future. So in other words, we no longer burn fossil fuels, we don't use oil, coal, natural gas, we don't produce cement. This would mean that the climate change would be very minimal between now and the end of the century. There'd be a little bit of warming up as the Earth equilibrated at the new temperature. Of course, this scenario is unlikely if humanity survives and we have societies in the future. Using more realistic social models, where we continue to use fossil fuels, produces higher temperature estimates. On average, however, scientists predict that the temperature will be markedly higher than it is today at the end of this century, especially over land and in the Arctic. This figure shows the world map with predicted increased totals. They're around 4 degrees Celsius, that is around 8 degrees Fahrenheit warmer than today. If you look at this map, you can see where you live. How much hotter is your place expected to be at the end of the 21st century compared to the beginning? 4 degrees Celsius is a lot. That's more than 4 times than we've observed over the 20th century, for example. This would suggest that the sorts of changes we've seen so far are going to be much smaller than the sorts of changes we're going to see from climate change over this century. So we're going to see very important consequential impacts from this increase in temperature. So these impacts will include a loss of permafrost, more loss of ice, including sea ice and glaciers, increased sea levels, increased land-based temperatures. Biological systems will have to change enormously, as will our farming systems. We might see places will get more or less precipitation than they do today, as you can see from the reading. This figure here shows a picture of a golden toad. Some scientists think that climate change in its natural habitat, the cloud forests of Costa Rica, is at least partly responsible for its disappearance. I wonder if the golden toad will be the first of many species that might be made extinct by climate change. So the burning of fossil fuels is having an enormous impact on the planet. Perhaps we can get away from burning so many fossil fuels by moving to a renewable energy future. In next week's lectures, we'll see if that's possible.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.